I'm presenting a multiple-choice question about using SGDRegressor, Stochastic Gradient Descent Regressor, from the SCIKITLEARN library in Python. We're focusing on how it behaves when the data has high multicollinearity, meaning features are highly correlated. The goal is to identify the true statements about the model's training and performance in this specific situation. This statement is true. High multicollinearity makes it hard to determine each feature's individual effect on the outcome. SGDRegressor, because of its stochastic nature, amplifies this instability. Small data variations lead to significantly different coefficient estimates. Think of it like trying to solve a puzzle with many similar pieces. A slight shift makes it very difficult to assemble correctly. I'll break down the problem into 4 steps to show how I determine which statements are true or false about the behavior of the SGDRegressor in the presence of multicollinearity. Here, I explain the core issue. Multicollinearity creates instability in the coefficients that SGDRegressor estimates. The algorithm struggles to distinguish between the effects of highly correlated features. This directly supports why statement B is correct. I'm setting up the scenario. We're using a specific algorithm, SGDRegressor, and our data has a serious problem, multicollinearity. The question focuses on understanding its impact. I'm guiding you through my thought process to analyze each statement regarding SGDRegressor behavior, which is vital for understanding the effects of multicollinearity. I'm about to explain my step-by-step solution to this multicollinearity and SGDRegressor problem, one step at a time. I'm using the SGDRegressor algorithm, which is a type of linear regression. But I have a problem. My data has a lot of multicollinearity, meaning my features are highly correlated. This will affect how accurately and reliably I can estimate model coefficients. I'm trying to train a linear regression model using SGDRegressor with data that has lots of correlated features. I want to understand how this multicollinearity impacts the model. Increasing the learning rate, or A to 0 feet, doesn't always mean faster convergence. It's a delicate balance. Too high, and the model bounces around wildly, never settling on a solution. Too low, and convergence is painfully slow. The best learning rate depends on the data itself, so I should carefully experiment to find what works. This is incorrect. Regularization techniques, like L1, lasso, or L2, ridge, are essential when dealing with multicollinearity. They help stabilize my model by penalizing large coefficients, preventing wild fluctuations caused by correlated features. Adding regularization makes the model more robust. This is true. Because of the multicollinearity, my model's coefficients will be very unstable. Small changes to my data can lead to massive swings in the values I calculate for those coefficients. That's a direct result of highly correlated features and the way SGDRegressor works. Although SGDRegressor is usually faster than batch gradient descent, it can still give inaccurate results because of the multicollinearity. So, I might see quick convergence, but the resulting model may not be accurate or reliable. We're using SGDRegressor, a type of linear regression model that uses stochastic gradient descent. The key here is stochastic, meaning it updates its parameters based on small batches of data, not the whole dataset at once. Multicollinearity means that some of our input features are highly correlated, which is problematic. For this model, I'm training a linear regression model using SGDRegressor on data with a lot of multicollinearity. I need to figure out which statements about the model's behavior are true. This means considering how multicollinearity affects its convergence speed, the stability of its coefficients, and the effect of regularization and learning rate. It's a conceptual problem, not a computational one. I predict the model's coefficients will be very unstable. Because of the multicollinearity, small changes in the training data can lead to big changes in what the model learns, its coefficients. That's what makes this statement true. Increasing ETAO, the learning rate, doesn't guarantee faster convergence. A high learning rate can cause the model to bounce around, never settling on a good solution. A low learning rate makes the process painfully slow. The optimal learning rate depends on the data. Regularization, L1 or L2, is actually helpful. In this case, it adds a penalty for large coefficients, thus stabilizing the model and helping it deal with multicollinearity. So, this statement is false. Even though SGD is often faster than other methods, multicollinearity creates instability. The model might converge quickly, but that doesn't mean the solution is accurate. The results could be very unreliable. I'm focusing on the impact of multicollinearity, high correlation between features, on the performance of SGDRegressor, a stochastic gradient descent algorithm for linear regression. I'll explore how multicollinearity affects model stability and the usefulness of techniques like regularization. I'm given a multiple-choice question about using SGDRegressor with a dataset that exhibits high multicollinearity. I need to evaluate statements about the model's training and prediction accuracy. Increasing the learning rate, A to 0, doesn't guarantee faster convergence. It's a balancing act. A high learning rate can cause the algorithm to overshoot the optimal solution, resulting in oscillations and failure to converge, while a low learning rate will lead to slow convergence. This is false. Regularization, L1 or L2, is precisely designed to handle multicollinearity. By adding a penalty to large coefficients, it shrinks them, making the model more stable and less sensitive to small changes in the data. This statement is true. Multicollinearity means features are highly correlated. In such cases, SGDRegressor struggles to isolate each feature's impact, leading to unstable and highly variable coefficient estimates. Small data variations result in significant changes to the model's coefficients. While SGD is usually fast, its stochastic nature doesn't magically solve the instability caused by multicollinearity. Quick convergence doesn't equal accurate convergence. In this situation, I'm using the SGDRegressor algorithm, a type of linear regression that uses stochastic gradient descent to model data. But there's a problem. The data has multicollinearity, meaning some of the input variables are highly correlated. This makes it tricky to pinpoint which variable is actually influencing the outcome. This is a multiple-choice quiz testing your knowledge of how SGDRegressor behaves when dealing with multicollinearity. You're training a linear regression model using the SGDRegressor function from scikit-learn's linear_model module. The data you're using has a major issue: multicollinearity among the features. The question is asking you to identify which statements about the model's training process and results are true, given this multicollinearity. Multicollinearity, in simple terms, means that there's strong correlation between different input variables in your dataset. Think of it like this: if I have two variables that are basically telling me the same thing twice, it's difficult to figure out their separate individual impact on the result. The SGDRegressor is a clever algorithm that's part of the scikit-learn library and helps us build linear regression models. It uses a method called stochastic gradient descent, which makes iterative adjustments to the model's parameters to find the best fit to the data. It works by looking at small random batches of the data at a time. With multicollinearity, a small change in the data could lead to a big shift in how the model assigns importance to each variable. That means the model's predictions become less reliable. It's like trying to balance on a wobbly stool. A tiny nudge can make it collapse. We're using SGDRegressor, a type of linear regression model from the scikit-learn library, and I want to point out that it uses stochasticgradient. The key here is multicollinearity, which means our input features are highly correlated. This is important because it impacts how the model behaves. I'm setting up the scenario. We're training a linear regression model using SGDRegressor on data where the input features are very strongly related to each other. This correlation between features is what creates the problem of multicollinearity. Think of it like trying to figure out if it was the sun or the heat that made you sweat. They're so connected it becomes difficult to tell them apart. This situation creates challenges for the model. I'm asking you to identify the true statements about what we can expect from our SGDRegressor model when it trains on data with high multicollinearity. We'll look at several statements and determine which one accurately describes this model's behavior. This statement is true. Because of the high correlation between features, multicollinearity, even minor data changes can significantly alter the model's calculated coefficients. It's like trying to balance a pencil on its tip. It's very unstable and susceptible to even the smallest disturbance. This is false. While stochastic gradient descent might seem to converge quickly, the presence of multicollinearity means that the solution it finds might not be accurate or reliable. The speed doesn't guarantee accuracy in this case. This is false. Regularization techniques like L1 and L2, lasso and ridge regression respectively, are specifically designed to handle multicollinearity. They add penalties to large coefficients, making the model more stable and improving its generalization performance. I would recommend using these. This statement is false. ETAO, learning rate, controls how big of a step the model takes during gradient descent. A very large learning rate can cause the model to overshoot the optimal solution and fail to converge. A small learning rate may lead to slow convergence. It's not a simple relationship. Finding the right balance is crucial. I'm using scikit-learn's stochastic gradient descent regressor, SGDRegressor, to train a linear regression model. The data I'm working with has a serious problem. Many of the input features are highly correlated. That's multicollinearity. I want to understand how this affects the model's training and performance. I'm looking for the true statements about what happens. This statement is true. Because of the high correlation between my input features, the model's coefficients, the numbers that tell us the importance of each feature, become very unreliable. Even tiny changes in the data can lead to big swings in the values of these coefficients. That's what makes them unstable. Think of it like trying to solve a puzzle with overlapping pieces. It's difficult to figure out which piece goes where. This is false. The learning rate, A to 0 in SGD controls how big a step the algorithm takes towards the best solution in each iteration. A higher learning rate might seem like it would speed things up, but it could also cause the algorithm to jump around wildly and never settle on a good solution. That's called divergence. Conversely, a learning rate that is too low will result in very slow convergence. Getting this parameter right is key. It's more of an art than a science to find the correct value. This is false. Regularization methods, such as L1 and L2 regularization, are designed to handle precisely this situation. They add penalties to large coefficients and this helps stabilize the model, improving both accuracy and performance when I have multicollinearity. It helps me avoid overfitting, the tendency to overemphasize noise in the training data. This is false. While SGD can be fast, multicollinearity makes the coefficients unstable. The model might converge quickly, but that doesn't mean it will be accurate or reliable. The instability introduced by multicollinearity overwhelms any potential speed advantage.